We will now cover Chapter 30, Chemical Kinetics. Chemists have three fundamental questions in mind when they study chemical reactions. First one is, what happens? That's your balance overall equation. What reactants are reacting to form what products? Second one is, how fast does it happen? What is the speed or reaction rate for a reaction? Does it take seconds? Does it take minutes? Does it take hours, weeks? This is what we'll be covering in this chapter. Third, what extent does it happen? Does the reactants form products to form 20%? Does it form 50%? Does it go to 100% completion? To what extent does the reaction occur? This is something we'll be covering in the next chapter. So this chapter deals with the second question, the speed or rate of a reaction, which is called chemical kinetics. Chemical reactions require varying lengths of time for completion, from milliseconds to weeks, maybe months, for a reaction to occur. The reaction rate, basically telling us how fast it happens, depends on the characteristics of the reactants and products and the conditions which under the reaction is run. Reactions act differently, depending on the reactants and products. If I have these reactants that react one way, if I have different reactions, it'll be a different reaction, different time. It all depends on the conditions of the reaction as well. What pressure, what temperature, these things affect the reaction rate. By understanding how the rate of reaction is affected by changing conditions, one can learn the details of what is happening at a molecular level. Basically, we're looking for what is the mechanism or the steps required for a reaction to happen. When you see a balance equation, say for instance 2A plus B gives me C plus D, it may be more complicated than what it appears. According to this reaction, it looks like I take two A molecules, they collide with a B molecule, and I form my products. But anytime you start getting to be three or more reactants colliding at the same time to form products, the probability of the reaction happen goes down. So when you start having more than three reactants, there's probably some mechanism or some step reaction going on. For example, in this case, there's a possibility we could be looking at this. Maybe the first step is that an A molecule collides with an A molecule to form an A2. That A2 molecule then collides with B to form the products. Overall, since your intermediate A2 cancels out, it looks like 2A plus B gives you C plus D. It gives the impression that two A's and one B molecule are colliding to form products, when in reality they're not. B collides with A2 to form the products. So this is what we mean by mechanism. There may be steps that occur, but when you look at all the steps together, the sum of the steps is what looks like your molecular balance equation. And we're going to talk more about this toward the end of the chapter. The question posed in this chapter that we will answer are as follows. How is the rate of the reaction measured? How do you express the relationship of rate to the variables affecting the rate? What conditions will affect the rate of a reaction? And what happens on a molecular level during a chemical reaction? Talking about that mechanism I just talked about a second ago. Well, since we're talking about chemical kinetics, we should define it, so let's do that. Chemical kinetics is the study of reaction rates, how reaction rates change under varying conditions, meaning how fast reactants are consumed and products are formed. Basically, another way of looking at it is a glass of water, is it half full or half empty? It's still the same amount of water. We can look at it in terms of how fast reactants are consumed or how fast products are formed. It's the same rate. Or what molecular events occur during the overall reaction. In other words, that mechanism, that pathway or series of steps for a reaction. The reaction rate is a positive quantity that expresses how the concentration of reactant or product changes with time. As I said, we can look at this in terms of consumption of your reactants or the production of your products. Either one, it's still the same rate. By definition, though, we're going to talk about it being a positive value when we talk about that rate. Okay, we'll only use negative sign in this case basically only to mean consumed, and positive to mean produced. But when I'm talking about rate, we always want a positive value. So we got the signs to use to decide if it's consumed or produced by Watson House signs, but it's not crucial in kinetics to worry about that, because by definition, it's a positive value for rate. That's not the case when we talked about thermochemistry. When you do thermochemistry, minus means exothermic, meaning release of heat, and plus means endothermic, meaning absorption. If you don't use the signs in thermochemistry, you can get wrong numeric values for your answers because the signs are not correct. It's not as big a deal here in kinetics. So by definition, what we're saying rate is your change in concentration over change in time. Okay? The delta sign basically means change. And typically what we do is we take our final value minus our initial value when we use delta. The brackets here typically indicate molarity, moles per liter, as our concentration term. So rate is your change in concentration divided by your change in time. We can put this in terms of products or reactants. So if we do it in terms of products, it'd be change in concentration of P divided by your change in concentration of T. Notice there's no sign there, because if you're talking about products, you're increasing by forming products, so your final concentration of products will be larger than your concentration of your initial products. So therefore, it will be a positive value, which will give you a positive rate. By definition, not a problem. However, when we talk about your reactants, you got to realize that your concentration of your reactants, your final concentrations, is going to be less than your concentration of your reactants initially. Okay, because you're consuming them as you go, which would mean then that you're going to get a negative value for your change in concentration of R. Well, by definition, rate's supposed to be a positive value, so we have a negative sign here to make that happen. A negative times a negative gives you a positive. Now, if you wanted, you could simplify this and not worry about signs and just look at it as an absolute value situation, and that would always give you the positive value. Let's consider the gas phase decomposition of dinitrogen pentoxide. Okay, I got two N2O5s going to four NO2s, nitrogen dioxide, plus O2. I can write this in terms of consumption of my dinitrogen pentoxide or the production of NO2 or O2 for my rate. I chose in this fashion to begin with. We'll talk about the rate of formation of just oxygen. I did that for a reason, because of the 1 coefficient in front of oxygen, which I'll explain later on as we go. So the rate of formation of oxygen can be found by taking the change in concentration of O2 divided by my change in time. It's a positive value because we're talking about the production. This equation gives the average rate over the time interval delta t. Okay, it gives me my average rate over that period of time delta t. If delta t is a very short value, you obtain something called the instantaneous rate. That is the rate for a particular instance. Okay, you got to realize that rate is changing over time. Okay, as we're going through this experiment, the concentration of your N2O5 is decreasing. Okay, what's happening here to form those products? I got to have dinitrogen pentoxide molecules colliding to form the products. As the reaction goes, that concentration of N2O5 goes down. Well, if the concentration of the species is going down, what happens to the probability of those two molecules colliding? That goes down as well. Well, if that probability goes down, then the actual rate will go down as well. So rate is something that is changing over time. Okay, continuously changes. You can only determine the rate over some period of time and determine what that rate is. Let's look at that in a graph. Over any period of time, say in this case delta t, okay, over some change in concentration, okay, over that period there is a rate associated with it. Okay, you can obtain that instantaneous rate from the slope of the tangent at the point of that curve. Okay, so we can determine that slope by the tangent of where it intersects that line. Okay, that's the rate over that period of time. If I was to do that a different time interval, okay, there'd be a different rate over that period of time. I could do it up at above here as well, and there would be a different rate for that period of time. So depending on what period of time I'm talking about, there's a particular rate associated with it. Now the rates at the lower end here, okay, this is going to be where I have a higher concentration of my reactant. So therefore, since it's a higher concentration, my rate's going to be higher than if I'm up at the top here, because my concentration of my reactants will decrease. Okay, so here I have a larger concentration of reactants, therefore it will be going at a faster rate. I have a lower concentration of my reactants, therefore it would be at a slower rate. Which I like to show you this through calculations on the next slide. For example, let's look at change of time between 600 and 200 and 1200 seconds. Okay, if I look at that, okay, at point 600 seconds, there's a molarity associated with it, and at point 1200 seconds, there's also a molarity associated with it, which is 0.0035 molarity. If I try to calculate my rate, which is change in concentration of O2 over change in time, I'll get 0.0035 molarity minus 0.0020 molarity divided by my change in time, which is 1200 seconds minus 600 seconds, which gets me 2.5 times 10 to the minus 6 molarities per second. Okay, that is the rate over that period of time. Let's look at a different period of time. Let's choose a period of time of 4200 and 4800. Okay. At 4200, we have a molarity of about 0.0072, and at 4200, we have a molarity at 0.0075. Okay. If we do our rate, change in concentration of O2 over change in time, we'll get 0.0075 molarity minus 0.0072 divided by our 4800 minus 4200, which comes to 5 times 10 to the minus 7 molarity per second. So the question is, are these two rates equivalent? And the answer is no, they're not the same number. So we agree that rate is changing over time. The other issue was we said that rate will be decreasing over time. Let's see if that holds true. Well, 10 to the minus 6 is larger than 10 to the minus 7. So yes, rate is decreasing over time. It is slower up at the top where the concentration has decreased. So that's the rate of reaction decreases as the reaction proceeds. Okay, let's try to sum up some of the things I said. Okay, first off, note that the reaction rate decreases as the reaction proceeds. That's important to realize. Okay, rate decreases as the reaction proceeds. The reaction slows down over time, therefore rate is time dependent. Okay, it's also concentration dependent as well. Rate is time dependent. It increases as reaction mixture runs out of reactants. Okay, naturally, concentration is less for reactants, therefore you have less collisions and slower formation of products. There's a smaller probability of a collision happening, therefore the reaction slows down. Rate is dependent on time. in concentration. Therefore, rate is changing over time. It is not constant for the whole reaction. Concentration affects the rate. As the concentration is changing, the rate will change as well. So it's not constant. It is changing over time. So rate is time dependent, and it is also dependent on concentration. Over any particular time, there is a certain concentration of reactants and a particular rate. Reactions occur as the result of collisions, so molecules, reacting molecules will collide. So therefore, the higher the concentration, the greater the probability of collisions, the faster the reaction. Okay, so higher the concentration, greater the probability of collisions, the faster the reaction. As reactants are consumed, their concentrations drop, the collisions occur less frequently, reaction rates decrease, basically eventually go into zero when all reactants are consumed. Or if it's a limiting reagent problem, at least one of the reactants is consumed. So the reaction continues to go, the rate will continue to drop as collisions become less frequently because the probability of collisions go down as the concentration goes down. Therefore, the reaction slows and slows down until it doesn't exist anymore. Because the amounts of products and reactants are related by stoichiometry, based on mole-to-mole ratios, any substance in reaction can be used to express the rate. So instead of going by the formation of oxygen rate, I could go by dinitrogen pentoxide if I wanted, which would be your change in concentration of your N2O5 over your change in time. However, since it's a reactant, I'm going to have to put a negative sign here to get my signs correct, because this is going to be a negative value, my change in concentration. So I need a negative to make it positive to get it in terms of a positive value. But it's a little bit more complex than that, because this is the rate of decomposition. But notice something. I formed 1 mole of oxygen, and I have 2 moles of N2O5 that's being consumed to form that 1 mole of oxygen. Things are going to have to be on a mole-to-mole basis. I'm going to have to account that I'm using twice as much N2O5 to produce half the amount of O2. Okay, so I'm going to have to account for that. Once again, note the negative sign. This results in a positive rate as the reactant concentrations decrease. Okay, we are describing the same rate, meaning if I can do it in consumption or production, it's the same rate, same value in terms of consumed to produce. Go back to my analogy of the the glass of water, half full, half empty, same amount of water, same quantity. Doesn't change, just a different way of looking at it. Same thing with rate. We talked about in consumption, I talked about in production, same rate. Just one way of looking at it versus another. However, the rates of production of your products and the consumption of reactants are equal, but on a per mole basis. Okay, your rate of consumption equals your rate of production on a per mole basis, meaning I have to account for the number of moles. Going back to our rate of decomposition of our N2O5, a reaction, I can write the rate equivalent to any one of these in terms of production or consumption. So you have your rate. I can write it in terms of rate is equal to the change in concentration of O2 over change in time. I can write it in terms of concentration change in N2O5 over change in time. I have to put in my minus since that's the consumption, it's a reactant. Or I can put it in terms of the production of NO2 over change in time. However, you got to realize I'm using different moles of these species. Okay, I have to account for that. So, rate is equal to the change in concentration of O2 over change in time. Okay, that's only 1 mole of the species. If I want to relate that to the change in concentration of N2O5 over change in time in a rate capacity, I have to account that I'm using twice as many moles of N2O5 by putting it in my denominator. Okay, it's being used twice as fast, so I have to account for that before I can compare apples and apples. Same thing for NO2, except that it's 4 times as much of NO2 being produced as O2. So once again, I have to put into my equation to get the rates equal on a per mole basis. So since 2 moles of N2O5 decomposes for each mole of O2 form, the rate of the decomposition of N2O5 is twice the rate of the formation of O2. We're using double, therefore the rate of the consumption doubles, and we must account for it. Let's put this in generic format. Let's say I just had a reaction. A plus B gives me C plus D, and I have the coefficients small subscript A, B, C, and D. Okay, I can write a general rate equation for each one of the species as reactants or products. Okay, all I have to do is put my change in concentration of my species over my change in time, and then account for the number of moles by dividing by it, and also accounting for the negative sign if it's consumption or positive sign if it's production. So looking at rate for this particular reaction, generic equation, I got change in concentration of A divided by change in concentration of T, but I also have this A factor that I got to account for and divide by it, and we also have a negative there because it's being consumed. It's one of the reactants. For B, same thing, change in concentration of B over change in time. I also have to put that negative because it's a reactant. And I have my B coefficient they count for. For my C and D, they've done the same way. I have my C and my D coefficients, but they have positive values because of the fact they are products. So basically I can compare my rates of my reactants or products, any species I want, just have to account the number of moles and also the minus or plus depending if it's reactants or products. Let's look at an example. Okay, given the consumption rate of N2 is equal to 0.10 molarity per minute, what is the consumption rate of H2? I want to know basically the delta H2, change in concentration of H2 over change in time. So basically my goal is I want to know what delta change in concentration of H2 divided by delta T is. Okay. Well, we know the reaction. We got N2 plus 3 H2s gives us 2 NH3s. Okay, so we have the reaction. I can relate rate between species. So if I do that, my rate will be my change in concentration of N2 divided by delta T, and the coefficient is 1. So it'll be divided by 1, and I have to put a minus sign there because it's being consumed. That's going to be equal to the rate of hydrogen, which we will express as delta change in concentration of H2 divided by delta T. And since there's a 3 coefficient, I have to account for that. And once again, it's a minus because I'm talking about being consumed. Now, from the information given, it told me the consumption rate of N2 is 0.1 molarities per minute. Well, that's given me my delta N, my delta change in concentration of N2 over delta T. But since it's a consumption rate, when I stick it in, I'm going to have to stick it in as a minus, okay, if I want to keep my signs correctly. Okay, so for my delta change in N2 over delta T, it is a minus 0.1 molarities per minute. Equation. So you have your negative 0.1 molarities per minute, and you have that negative to change the sign, which now makes that a positive 0.1 molarities per minute. We're going to multiply by 3 on both sides. So now that gives you 0.3 molarities per minute. And then we've got to bring that negative sign over from the delta H to the other side, which gives me a negative 0.3 molarities per minute. So when you submit your answer, though, it won't be a negative 0.3, it'll be 0.3. Because by definition, rate is a positive value. That negative sign is just telling me that that hydrogen is being consumed, which I already know because it's on the reactant side of the equation. Now, we could easily have done this problem slightly different if we wanted. Okay, this is rate, it's how it's done with kinetics, but you can go back to your Gen Chem 1 stuff and also do it on a mole-to-mole basis. We know that we have a negative 0.1 molarities per minute of nitrogen. Okay, and there's a relationship between nitrogen and hydrogen with our 3 to 1. Okay, so we also know that there's, for every 1 mole of nitrogen, there's 3 moles of hydrogen. Okay, so your moles cancel and you get a negative 0.3 molarity per minute of H2. which is the same answer. So you could still do this as stoichiometry if you wanted, stoichiometry basis if you wanted as well. Homework number 5, there's questions dealing with rate.